Hi everyone, my name is Mehrnoush Kapoor and I'm going to present my paper, which is a lightweight survey on techniques to formally model human behavior in collaborative robotic applications, where physical safety is of utmost importance. So let us start with a little bit of a background on human-robot collaboration. Traditionally, robotic systems in manufacturing settings used to work in fenced areas apart from human operators, and thus benefiting from both human flexibility and machine productivity was quite challenging. Human operators were only allowed to enter the workspace of robots when they were completely idle. Nowadays, robots have evolved in size and functionality so that they are capable of collaboration and close interaction with human operators. This would facilitate the combination of human flexibility and machine productivity, but obviously introduces new safety concerns due to close vicinity and frequent contact between human and robots. Like many other safety critical systems, human-robot collaboration needs to go through a rigorous safety assessment prior to mass use. It is therefore important to predict all the situations that could challenge physical safety of human throughout the collaboration. For example, the environment is dynamic and can frequently change due to mobile resources or changing parts or tools of the robot. The coexistence and vicinity of human and robot in common workspaces also could lead to dangerous or accidental contacts. And finally, the on-the-fly decision-making of human operator on how to execute hybrid tasks, that is, which part is done by the human and which part by the robot, could also create multiple possible traces of the execution, of which some could be dangerous. Common methods have been widely used in robotics for decades in a variety of applications, including mission planning from a verification of properties or controllers. Moreover, they proved to be effective means for the safety analysis of traditional or collaborative robotics due to their comprehension and exhaustiveness. They also allow for incremental model updates and iterative property verification. However, a formal model of an HRC system should reflect the human factors that impact the state of the model, which requires building a formal model that replicates the physical presence and the observable manifestation of their behavior. That includes both executing the required job following the expected instructions or any deviations from the expected instructions. This paper explored the state-of-the-art solutions for modeling human and discussed their limitations and benefits for HRC scenarios. Following a snowballing approach starting from a couple of extensive survey papers that are mentioned on the slide, three main trends of modeling techniques have been identified: cognitive investigations, task-analytic models, and probabilistic approaches. In this work, we discussed 39 papers that have applied human modeling. There are many more relevant references in the paper that describe the approaches or provide hints to surveys or different versions of models, but 39 of them are examples of applying human modeling techniques. As you can see on the diagram, 17 of them are examples of cognitive models, 19 of them are task-analytic models, and 10 of them are probabilistic. And as shown on the diagram again, the classifications are not mutually exclusive, meaning that some of the papers could have been classified as instances of more than one category of models. Three most well-known cognitive models in the literature are introduced here. SOAR was introduced initially in 1992. Since then, there are several updates and improvements on the model. References could be found in the paper. In general, SOAR is an extensive cognitive architecture relying on artificial intelligence principles that reproduce human reasoning and short and long-term memories. The second well-known model is ACTR, initially introduced in 1996, again with several improvements since then, which is a detailed and modular architecture that depicts the learning and perception processes of human. It contains modules that simulate declarative and procedural aspects of human memory. Declarative aspects are known facts like 2 plus 2 is 4, and procedural aspects are, for example, the knowledge of how to sum two numbers. The third one is Programmable User Model, which initially introduced in 1997, defined a set of goals and actions for human. The model mirrors both human mental actions, like deciding to pick an object, and physical actions, actually picking an object. These models have a notion of human mental model and separates the machine model from the user's perception of it to avoid mode confusions which happen when the observed system behavior is not the same as what user actually expects. Several references to examples of the use of each of these models could be found in the paper. Overall, the 39 papers that we have analyzed, around 45% of them discussed cognitive models and their variations or simplifications. Around 5% talked about SOAR, 13% used ACTR, and around 18% used PUM. 8% of works have used simplified or customized cognitive models that have used principles of these established cognitive models or have been inspired by them. Cognitive models are obviously capable of replicating the proactive presence of human in the task execution and also their errors. However, there are a few non-negligible issues. SOAR model permits only one operation at a time, which seems not to be realistic enough for HRC scenarios. Simply assume a situation in which the human sends a signal while moving towards a destination. SOAR and ACTR both lack a formal definition, therefore they must be transformed into formal models, which is a cumbersome and time-consuming process and requires extensive training for modelers. All three of the models are detailed and heavy, and therefore must be abstracted before formalization to avoid state space explosion. There are examples of works that try to abstract and then formalize these models. They are referred in the paper. However, they are too case specific and not generic enough to be used for different scenarios. Now let's get into task-analytic models. Task-analytic models analyze human behavior throughout the execution of the task. Therefore, they study the task as a hierarchy of atomic actions. By definition, these models reflect the expected behavior of the human, which leads to correct execution of the task, and do not focus on reflecting errors. However, some more recent works try to include errors and model them as divergence from task models. Examples are cited and briefly explained in the paper. There are several hierarchical notations, of which two more common techniques are concurrent task trees and enhanced operator function models, each with their own defined notation and semantics as shown in the figures. CCT is a notation for task model specification useful to support design of interactive applications specifically tailored for user interface model-based design. And EOFM is a generic XML-based notation to gradually decompose tasks into activities, sub-activities, and then atomic actions. Over 39 papers, almost 48% was on task-analytic models. They used enhanced operator function model and its extension enhanced operator function model with communication, CTT, operator choice models, finite state automaton, user action notation, and some of them use their own introduced models or combinations of existing models that we just mentioned. Examples and explanations of each of these models are presented in the paper. Task-analytic models depict human-robot coexistence and highlights the active role of humans in the execution of the task. However, they do not always reduce the overall size of the state space of the model, especially when multiple human operators are involved in the execution. Moreover, they do not offer reusability because they are very much dependent on the case study scenario and its executing task, and consequently not generalizable. Also, most of these models do not generate erroneous human behavior. Another approach to reproduce human non-determinism and uncertainty more vividly is probabilistic models. Unlike deterministic models that produce a single output, stochastic or probabilistic models produce a probability distribution, and in theory, a probabilistic human model could be very beneficial for model-based safety assessment in terms of a trade-off between cost and safety. System engineers could have some estimation of the probability of occurrence of a hazard when thinking of a potential mitigation strategy. Around 24% of the papers we considered discussed probability, some of which used well-established techniques as shown on the chart, and a large portion of works had their basis on the use of Bayesian networks. Of all the papers that used cognitive models, none of them tackled probabilities, and only 25% of task-analytic models that we've analyzed did use probabilities at some level. Probabilistic models seem to be an optimal solution when combined with task-analytic or cognitive models. The problem of choosing a probability distribution remains an issue, though. The current works that we've analyzed use different probability distributions to represent human model, but there's no guarantee that these probabilities actually represent human behavior in a realistic way. The problem here is to have reliable and large enough data sets to extract the parameters of probability distributions from. And that is possible when the robotic community care for producing huge training data sets from their system history logs that contain information such as how frequently human operators move in the workspace, the average value of human velocity while performing a specific task, the number of human interruptions during the execution, and other information like this. Human operators are prone to errors that are activities that do not achieve their goal. They could be a very significant source of physical hazards in HRC scenarios. So a realistic human model for safety analysis purposes shall be able to replicate errors too. One must first recognize what are those errors and settle for a precise definition for them to be able to model them though. Although there is no widely used classification of human errors, some of the works done on this topic stand out and provide a general overview that is usable in different application domains. For example, Reason in 1990 divided errors in three main categories of behavioral, contextual, and conceptual. In 1998, Holnagel introduced some general common patterns of human errors during task execution that are repeating, reversing the order, omission, late or early execution, replacement, intrusion of actions, and inserting an additional action from elsewhere in the task. Serron in 2005 used temporal logic to model human errors that are defined as fail to observe potential conflicts, ineffective or no response to observed conflicts, fail to detect the criticality of a conflict. Shin et al. In 2006 divided errors into two main groups of location errors that happen when humans shall find a specific location for the task, and orientation errors that happen due to humans' various timing or modality to perform a task. More details on these classifications and several other examples could be found in the paper. The error definition is context dependent and might vary from one domain to another. Field's classification is comprehensive enough for possibilities in HRC scenarios. There are three levels of definitions in his model, starting from error modes, which are actions in wrong place or time, not predicted actions, or in wrong type. Simple and complex phenotypes are derived, each describing different undesired situations. More detailed explanation on each of these phenotypes is provided in the paper. Even though modeling errors is very essential to have a realistic representation of what happens in practice, as you can see in the chart, the majority of papers did not take them into account, in particular task-analytic models, because these models are very dependent on the task definition and inherently do not consider errors. Not all of the human reactions and possible errors are predictable, of course. However, modeling a reasonable set of errors that can frequently occur throughout the execution of a task could considerably improve the quality of formal verification results that are used for physical safety analysis. As we've seen earlier, no unique terminology is used, at least in the robotic domain, for these errors. An attempt to resolve this issue would be for standard organizations to introduce a list of the most frequent human errors in certain applications. It needs sort of data sets that we said are needed also for probabilistic models, so the same concern is true also here. Here are a few conclusions from this presentation. The details included in the cognitive models on the cognition process behind human acts is not necessary to be included in models, at least for safety analysis purposes, since what we care about is the consequence of their acts and not their motivations. Cognitive models are usually not in an acceptable shape for automated formal verification tools and need a great deal of work for their formalization. Still, POM models seem to be more easily tailored and formalized for different scenarios, and there are actually more instances of their use in this context. Task-analytic models are very dependent on the scenario they represent, and those are not usually reusable for different scenarios. However, these models break down the execution into pieces or atomic actions and enable us to analyze the interrelations between those actions. And it becomes easier to define deviations from correct execution of those actions, which are technically errors. Then adding probabilities to these deviations would make the model more realistic and allows us to regenerate and analyze many situations that actually could happen in practice. Thank you for your attention. I'd be happy to answer your questions or receive any feedback. Thank you.